Hello everyone, I'm Paul and today we're solving problem 417, Pacific Atlantic water flow. This is an interesting mean one, and here we show you how to solve this visually first, and then we will go with the code. We are given a matrix such as this one with different heights. So for example, this cell is higher than this one, and it rains a lot. Here we have an island and it rains a lot in this island. And the water can flow in the four directions. It can go up, down, left, or right. And we have the Pacific Ocean that's here in the left and top, and the Atlantic Ocean, which is in the bottom and right. So let's say we are here. Water can flow to heights that are less than or equal to the current height. So if we are standing at 5, water can flow here because we have a 4, it can flow here also, and it can flow to the Pacific Ocean. We are right next to the Pacific Ocean, and it can also flow to the Atlantic Ocean because we are right next to this ocean also. And our job is here. We need to return an array result where each element represents the coordinates for every cell from which, when it rains, we can reach the Pacific Ocean and the Atlantic Ocean. So we need to add the coordinates for this cell, for example. This is row 0, 1, 2, 3, 4. And for the columns, we have the same. This cell belongs to row 0, column 4, so we need to add an array with 0, 4 to the result. Let's say we're here, we are right next to the Atlantic Ocean, and we can reach the Pacific Ocean because we can move to heights that are less than or equal to the current height. So we can go here, then here, then here, for example. So we can reach both oceans, so we add the coordinates for this value, which are 1 and 4. That's why here in the result we have 1 and 4. And from here, 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 and here, we can also reach both oceans, Pacific and Atlantic. So the final result is this output. We need to return an array like this one. Now maybe you're thinking about trying a BFS from every cell. Let's say we are here, and remember that in BFS we are moving in circles, and by doing this we can check if we can reach both the Atlantic and Pacific Oceans, and if we can, we add the corresponding coordinates for the current value to the result. Now this is fine, but we need to run a BFS from every value, and this is a lot. We need to find something more efficient. And the trick here is the following. Instead of going from every cell to the oceans, we are going from the oceans to the grid. So we need to run the same BFS exactly twice. First we will have the Pacific Ocean at the source and then the Atlantic Ocean at the source. Let's say we start here with the Pacific Ocean. We have a queue. Remember that we use queues for BFS, and first we are adding every value in these two borders, left and top, to the queue. So we are using green for values that we have already seen. And from each of these values, let's say we are standing here, we are checking every neighbor. Given that here the neighbors are 3 and 2, these are part of the border, we can reach the Pacific Ocean from any of these values in these two borders, so we continue. Now let's say we're here, we are checking every neighbor, this and these are part of the border, and this is a new value. And given that this is also a 2, meaning this and these are equal, water can flow from this cell to this cell. So we can add these to the set. Let's say next we are here, this and these are part of the border, this is a new value, and it happens the same here. This value is higher than this one, so water can flow from this cell to this cell. So we can add this to the set also. And now I think you get the idea, so I will fill the rest of the values for the set. So now these are all the values in the set, and we can run the exact same BFS for the Atlantic Ocean. So we do the same as before. First we add every value that's in these borders, and we have a new set. So first we have this in the new set, and we need to follow the exact same process. So for example, water can flow from here to here, so we add this to the new set. We need to add this because water can flow from here to here. We also can add this, and of course we can add this, and this. And here is all the information we need. For example, here we have this element in both sets, so we can add the coordinates for this element to the final result. And we are doing the same for every element that's in both sets. So we need to get the intersection of these two sets, and the coordinates for these elements is the result. So this is basically the entire approach. And with this in mind, let's go with the code. First we say n is the length of heights, m is the length of heights at 0. And now we can build our BFS function, and this will take a source as an argument. First we have a queue, which will actually be a deck in Python because we need to pop elements from the left. That's what we do with BFS. And if the current source is P for Pacific Ocean, we need to add the corresponding borders for this source. So for I in range n, q.append a tuple with I and 0, and for the other border for I in range m, q.append a tuple with 0 and I. Else, meaning the source is the Atlantic Ocean, we are adding bottom and right border in this case. So for I in range n, we add I and m-1, and for I in range m, we add n-1 I. So now we can build a set. We will call this scene. This is a new set, and we are storing here initially the current border. And while we have something in the queue, q.popleft, and this will give us two values, I and j. And now for every neighbor, meaning new I, new j in I plus 1 j, I minus 1 j, I j plus 1, and I j minus 1. First we are checking if we are out of bounds. So if the new I is more than 0, or new j is more than 0, or this, we just continue. Okay, so if we are out of bounds, we continue. If we are still here, we need to check if the water can flow from the neighbor to the current cell. So if heights new I new j is greater or equal to heights ij, and not new I new j in scene, if we haven't used this neighbor yet, meaning we can use it right now. So if we meet these conditions, we can add to scene, new eye, new shape. We add to the queue the same. And after all of this, we can return scene. So now we have our BFS function and we can go with the next part. And first we'll say set P is BFS and the source is P for Pacific, and set A is BFS with A as the source. And now we need to find the intersection of these two sets. And there are basically two ways to do this. Here we can just return list set P intersection. This is intersection for sets, set A. So let's submit this and see if it works. Here I'm missing an A, so let's try again. As you can see, this works and it's very efficient. There's another way to do this. We can say the result is an empty array, and for x in set P, for y in set A, if x is equal to y, result.append any of these two. Let's say we add x. And this is fine, but this requires big O of n square time complexity. So this is not very efficient. This is more efficient. This requires big O of n time complexity. So overall time complexity for this approach will be big O of nm, and space complexity is the same. So this is it for this problem. If you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.